Welcome back everyone. So today we're going to start lecture number 15, and the topic for today is basically what's left of reinforcement learning for the purposes of this course. We're going to wrap up reinforcement learning today. So first we're going to discuss learned models. We're going to do this first, and then talk about extensions of the methods we've seen to continuous state settings. And we're going to cover two topics over there: discretization and fitted value function or iteration. And once we are done with these two, that basically marks the end of what's part of the syllabus for this course, the parts that you'll be tested on. And for the rest of the lecture, once we are done with this, we will do a quick survey of the larger reinforcement learning field in general. Just talk about the different kinds of approaches that are there in reinforcement learning that we are not covering, and kind of give you an approximate mind map of how to kind of relate all the different concepts in RL to each other. Right. So before we jump into today's topics, let's do a quick review of what was covered on the previous class on Wednesday. So we started off with a formalism called Markov decision processes, where this formalism describes the setting in which there is an agent that is making sequential decisions over time, and an MDP or a Markov decision process is a tuple of 5 entities. So first is a set of states, set of all possible states that the agent can currently be in. A is the set of all actions that an agent can take. For simplicity, we'll assume that all actions can be taken in all states. PSA is what is called as the transition probabilities. So transition probabilities is we have a set of transition probabilities for the set of all states and the set of all actions. What that specifically means is the transition probability is each PSA is a probability distribution over the set of states, and it is different for every combination of S and A. So if we are in current state S and we take current action A, then the state that we will end up in for the next time step is distributed according to PSA. Right? So this is only describing how the world works. Right? Think of this as like the laws of physics. You take an action and you end up in some state. This is how the world works. Right? And gamma is what we call as a discount factor. It's a value between 0 and 1. And R is it's a function. It can either be a function of state or a function of a state and action pair, and it is the immediate reward function. What is the immediate reward that we get for being in a particular state? Right? And there are these two central concepts in reinforcement learning that's beyond the MDP formalism, called the policy and the value. Right? These two are kind of you can in a loose sense you can think of them as the duals of each other. Right? So the policy basically is the rule book that the agent follows. Right? It tells us when we are in a current state S, what is the action that we need to take, and the action that we take based on the policy will decide which new state we'll end up in based on the transition probabilities. Right? So the policy is just a rule book of what action we need to take when we are in a particular state. Right? And the value function is like the long-term accumulated or the expected long-term accumulated reward along with the discount factor gamma. So the V pi of S is the expected sum of all rewards, that is the reward at current state plus a discount times the reward at the second state plus a discount square times the reward at the third state, and so on. And it is the expected sum of these future rewards, discounted future rewards, assuming we are starting at a state S naught equal to the point where we are evaluating the value function, and assuming we are following some particular policy pi, right? And this is also called the Bellman's equation, and this expected sum of future rewards can be expressed this way according to the Bellman's equation. There was a question from some student about how we go from here to here, and there is a short derivation that I posted on Piazza number 240 if you want to see how we went from here to here. It's pretty straightforward. Now, there was also a question of gamma yesterday. Should it be the same value? Should it be less than 1, and so on? The answer is it should be less than 1, strictly less than 1. It cannot be greater than 1. And it is this gamma that is less than 1 that makes the value function bounded, right? So it's easy to see. If supposing gamma was equal to 1, then in general we could have accumulated, we can keep accumulating rewards by an infinite amount, and in general the expectation need not be bound, so, right? The expected sum of all future rewards can explode to infinity. But because we have this discount factor gamma, which is mostly here for mathematical reasons, just to make the value function bounded, but it also so happens that it has nice interpretations, such as the interest rate and whatnot, if you're working in an finance setting, or you can think of it as the rate at which your robot's fuel is decreasing or whatever. So you can have different kinds of interpretations for gamma, but it exists mostly for mathematical convenience to make the value function bounded. And the reason why it's bounded is pretty simple. You can see that this expectation is going to be less than it's going to be we can show a quick proof here. So this expected sum of rewards R of S1 plus gamma times so on will be less than expectation of, I'm just going to call it R star plus gamma times R star plus gamma square times R star, etc., where R star is the maximum possible reward that you can get in any possible state. And once you have this, you can take R star common and you get a 1 plus gamma square and so on. That is bounded. So the expected sum of all future rewards will always be bounded if we use a gamma of less than 1. Right? And then based on these two central concepts, policy and value, we can define something called as the optimal value function. So the optimal value function is the best possible long-term value we can have if we were to choose a suitable policy. So if we were to optimize over all the possible policies that can exist, what is the best possible future long-term value that we can come up with, right? And this is similarly, we can see that V star S is equal to can also be written as R of S plus max of A of this term. And you can see that this is pretty intuitive. What this means is V star of S is the best possible long-term value is equal to the sum of the current value that we got. That's immutable. The reward that we got at the current step is the reward that we got at the current step, no matter what our policy was. Right? And choose. This is a recursive definition, and choose an action such that we maximize the long-term reward at the next time step. Right? So depending on which action we choose, we get a different probability distribution for the future, a different transition probability distribution, and take the expectation of the next time step according to the probability distribution. So max is basically the max operator is choosing different transition probabilities essentially, right? Choose an action such that the resulting transition probabilities will give you the highest expected reward, expected future value at the next time step, right? So it is this recursive definition, which also happens to be called Bellman's equation, confusingly. This is also called the Bellman's equation. And the corresponding to the value, the optimal value function, there is this implicit optimal policy. So the implicit optimal policy is any such policy that allows us to achieve the optimal value function. Right? In theory, it is possible that there exists multiple policies. So strictly speaking, this should be element of the set of argmax, because this argmax, so probably this should not be element. Yeah, so this should be an element, because there could be multiple actions that you can take in any step that gives you the optimal, that maximizes the future value. But for the purpose of this course, we'll assume that it is unique, right? And it is this optimal policy that is kind of our, that's our end goal. That's what we strive to achieve. And when we say we want to solve an MDP, it means we want to find the pi star, the optimal policy that, in some way, right? And that's called solving an MDP. Right? And then we we saw the relation between policy and value, right? The policy and value are kind of, they have this intimate relationship where given a policy pi, there is a corresponding value function that you achieve by just following that policy all the time, right? And we saw this derivation last time where given a policy pi, there is an associated v pi that can be derived in this way, where this is the identity function and p pi is the transition matrix, where for each state we choose the corresponding PSA according where the a is taken from pi, and so from pi we can recover a v pi this way, and this is called policy evaluation, right? That's one direction. The other direction where you're given a value function, right, and this value function induces a policy which is also called the greedy policy with respect to v, right? And that policy is basically at any given state s, choose the action, the action that is prescribed by this policy is basically the action that maximizes the expected value of the next time step, where the value is defined by the given value function, right? So this we can go between policy to value and value to policy using these two relations, right? A subtle point to note is that given a policy, we get a corresponding value function that's kind of associated with this policy. However, a subtle point which may not be obvious at first sight is if we were to take this policy pi that was induced in this greedy way from this value function, right? If we were to follow this policy, the resulting value that we get is not this value function. It may be a different value function, right? That's a subtle point. A value function induces a policy, but if we were to follow this policy, it is not, we will not get the same value function. We need not get the same value function, right? And that's a subtle point, and that's something that we're going to see in policy iteration, right? And we saw one algorithm of solving MDPs, where the first algorithm we saw was value iteration. Now in value iteration, it is an iterative algorithm, it's called value iteration. It's an iterative algorithm where we start at some arbitrary value function. It could be the value function is equal to, you can either set it to all zeros or you can initialize it to the reward function itself. You start at some value function, right? And we iterate it over and over, where we take the value function of the current iteration and run it through something that's called the Bellman backup operator, right? And we get the next value function, and then we plug it in and get the next value function, and so on. And the Bellman value operator is defined in this way. So the Bellman backup operator is if this is v prime of s is equal to, where v prime is Bellman operator on the previous v, so the value function for the next time step is equal to r of s plus max of whatever expression here, and this thing here is basically the right hand side of the optimal value function, right? And this is called the Bellman backup operator, and we run this algorithm in a loop and iteratively until we converge on a v function, where v function stops changing. And once we get that v function, we can recover the corresponding policy using this expression. So given a v that has converged through value iteration, recover a policy, and that's our optimal policy. That's our solution to an MDP. And the reason why this converges, we saw that it is possible to show that this Bellman backup operator is what is called as a contraction mapping. So if we imagine the space of functions, a functional space, where each point here defines a value function, a point here represents an entire value function, where the coordinate of that, where a coordinate along a particular axis is the value of the value function along that state, right? And the Bellman backup operator is a contraction mapping, which means if we take any two value functions, run the two of them through the Bellman operator, right, the distance between the outputs will be closer than the distance between the inputs, right? That's why it's called a contraction mapping, because as you apply points through the Bellman backup operator through this contraction mapping, they get closer and closer, right? And the point at which they converge is called the fixed point of that operator, and that fixed point is v star, right? That v star is the optimal value, right? And then we saw this other algorithm called policy iteration, right? So this is one possible algorithm for solving an MTP. This is another algorithm for solving an MTP. And in this algorithm, we basically exploit the subtlety that I mentioned earlier, that from a given pi, we get a corresponding v, where this v is the value that you get by following the policy pi. However, there is a way from which, the other direction, where we recover a policy by using the guidance of some value function, right? We use this value function estimate to choose a particular policy to do where we strive to do better, where we strive to do our best given the current policy. And using this policy, if we actually use this policy, the resulting value function may be different, right? And that is the subtlety that we use over here. So start with some randomly initialized policy. So random init of pi, right? And from this random initialization of pi, we do step 1. For a given pi, we use we calculate the corresponding value function, which is what we call as policy evaluation, right? And once we get the policy, the corresponding policy v pi, we get, we try to calculate the optimal policy for this v pi, right? And we do this over and over until pi converges. And this is called policy iteration. And the converged pi will be pi star, right? And once we get pi star, we can again recover v star, and the pi star and v star that we get from this algorithm and the pi star and v star we get from this algorithms are essentially the same, right? So this is how much we covered in the last class. Any questions on this before we jump into today's topics? Right, cool. So today we're going to start seeing extensions of these methods. So the first extension we're going to see is what happens when we don't know PSA. What happens when PSA is not given. Right? So this is our first extension, and this corresponds to section 3 in the notes. Learning a model for an MDP. So here, when we in reinforcement learning, when you see the literature, when you read textbooks and papers and so on, you will see this terminology called model-based versus model-free. Right? So over here, in this terminology, model does not mean the model that we are constructing, right? So model over here refers to the model of the environment, or model of the universe in which the agent is operating, right? That is the model that this is referring to, right? And this essentially means here model means PSA. Now, if you know PSA, if you know how what state you might end up in depending on what action you took, it means you know how the environment works, right? You have a model of the environment. That's what this model means, right? Now, PSA is also called the model, and the first topic that we're going to cover is learning a model. Again, here by learning a model, I mean learning PSA. So, supposing we don't know how the how the transitions work, we don't know what state we might end up with, and supposing just assume PSA is not given, what do we do? And when PSA is not given, the one thing that we can do is basically, assuming we have some kind of a simulator where we can run these experiments, run multiple trials, right? Run multiple trials, where in each step you start at some state S0, take a random action, A0, you end up in S1. take another random action, S2, and so on, and then repeat a trial, S0. And so on, right? So each horizontal line corresponds to one trial, right? In the homework that you will see, that will be releasing on Monday, so you can think of each trial. So the homework problem is about balancing the cartwheel or the inverted pendulum, where the goal is you're given a stick, and you need which has 1 degree of freedom, which can move around, and it's balanced on a cartwheel. The cartwheel also has 1 degree of freedom, and you need to keep moving the cartwheel to keep the stick balanced upright, right? And a trial in such a case would be starting at some initial configuration, an initial position, an initial angle of the stick, an initial velocity of the cart, and the actions in that case would be to move the cart left or move the cart right? So take some random action starting from some initial state until the stick falls down or some such terminating condition, right? And then start over again with a different starting state, and take different actions. You may be following some particular policy, you may be taking random actions, it does not matter. We are basically exploring the environment, we are learning the environment, right? And take some such actions like this, and then construct estimators for PSA from this. So P, I'm just going to call it P hat SA of S prime is equal to the number of times we took action A at state S and got to state S prime over number of times we took action A at state S, right? So run such trials, lots and lots of them, and once you run all these trials, we just count the number of times we were at state some particular S and took a particular action A, and that goes into the denominator, and the number of times when we took that action in that state, what fraction of times did we arrive at state S prime, right? So this is the simple maximum likelihood estimator of the transition probabilities, right? And it might so happen that sometimes both of these could end up being 0 over 0, right? We saw this in naive Bayes when you're trying to get maximum likelihood estimates based on counts such as this. It may so happen that for some of the cases we may have 0 over 0. In those cases, it is common to a common practice in such cases when we get 0 over 0 is to assume a uniform distribution for P of SA, which means if we have never reached the state S and taken an action A from state S, just assume that we are that we're going to uniformly end up in any one of them. Now the moment we actually end up taking an action at state S, we can then update our counts to reflect what the actual distribution was. The moment we reach a state S and perform an action A, the denominator is no longer 0, it will be 1, right? And then we won't have the 0 over 0. Until then, it's common to assume a uniform action assume a uniform distribution over the future states. Okay. And using this kind of an estimation of the states of the transition probabilities, we can now construct an algorithm that looks like this. So this is an algorithm with model learning. Again, here by model I mean PSA, the transition probabilities. Right? So initialize pi randomly, right? Now to repeat execute pi for some time, right? Which means basically, step 1 or 2a rather, 2a, right? So run a few trials where the actions you're choosing are based on the random initialization of pi. B, using these trials, estimate p hat of SA. Okay? And by estimate p hat of SA, basically this means estimate S times A number of probability distribution, where each distribution is over all the future states, right? This for each S comma A, right? So there are S times A number of such probability distributions. So estimate all of them. And C, apply value iteration. I'm just going to write it as VI. Value iteration using p hat SA. Using p hat SA to get updated V, let's call it VT, right? And D, update pi to be greedy with respect to VT, right? So what's this algorithm telling us? Start at some random initialization of policy, some random policy, right? And follow that policy for some time. And by following this policy for some time, basically what we are trying to do is not only learn an estimate of our value function, but we are also learning PSA as well, right? By following some policy, we are learning how the environment works. You take some action from a current state, you end up in some new state, right? And you keep observing that again and again. You tend to learn how the world works. You tend to learn how the dynamics of the system works, right? And that's like a separate task from estimating the value function, right? Learning how the dynamics of the environment works is a separate task from learning the value function corresponding to that policy, right? And using this experience, we can estimate p hat SA. It's important to note that learning p hat SA is independent of the policy that we were following, right? And in fact, what we can do is to estimate p hat SA in each iteration, we can actually use the accumulated counts from all the previous iterations as well to get a better estimate of the p hat SAs, right? And using the estimated p hat SA, we perform value iteration. Now what was value iteration? In value iteration, to remind you, this was value iteration. in value iteration, we basically loop, so this line over here, apply value iteration, means perform this loop until convergence, right? So step 2c is actually a full loop of value iteration, and in this value iteration, we see that we need to take an expectation as part of computing value iteration, and it is for this expectation where we use the p hat essays instead of p essays. We don't know PSA, we are using data to construct an estimate, p hat essay, and it is this p hat essay, estimating this p hat essay, that we call as learning a model, right? We use the estimated dynamics of the environment to perform value iteration and reach some V star. So it is the V star of that particular iteration, and the V star will change from iteration to iteration of that algorithm because we are using different dynamics in each iteration. Yes, question?
Why don't you just remove step C and D out of the loop and do it later? So first, just keep playing and estimate all the p hat essay for all possible S, and then after, once you have good estimates for all p hat essays for
Good question. So the question is, why not just perform A and B over and over until we are satisfied, and then do C and D? The reason why that might not work all the time is because unless you have a good policy, you may not even reach certain states.
But you have to, to be able to understand the game well, you have to exhaustively search the S, A space, right?
Yeah. So the question is, we need why not exhaustively search SA, all the states and all the actions, all tuples, and the reason that might not be possible in practice is because we may not be able to arbitrarily choose an S of our choice, right? We may be limited to start from certain starting initial states and explore by taking actions. It may not be possible to say, I want to start at some particular state at some time, and to exhaustively try all possible S and A sequences can be exponentially complex. You may not be able to do a brute force and do a full sweep. That could take that could be exponentially logical. It could take years, for example, right, to do a full sweep of the entire state and action space. And that's why we follow this iterative approach where we try some initial trials for some policy, get an estimate, and then perform value iteration and use that value iteration to drive the exploration in the next state, right? Yes, question?
So you said one of the problems with what I said was that you can't, to estimate p hat SA, to exhaustively search it, you need to start at different S's, but we don't have exact control over that. But we can still use our whole episode, let's say, we can use substrings of it as episodes, right? If you start from state 1, 1, and then in the middle you go to state 5, 4, and then the end state is 9, 9.
Yep.
You can use part of those episodes as new episodes, right?
So the question is, can we use parts of episodes as new episodes? And the answer is, to calculate this, we are only calculating these links at a time, right? We take S, A, and S prime and count them to estimate this. So when we are estimating the probabilities, we take all the episodes that we have and only look at every consecutive S, A, S prime triples. Right. So this is an algorithm that we get where we are simultaneously performing value iteration and also learning the dynamics of the system. So at this step, we will achieve the optimal value function assuming a certain given dynamics. Right? For this particular dynamics of p hat SA that we've learned, the resulting V at the end of one loop of this algorithm will give us the V star corresponding to that p hat SA. Right? But that p hat SA might not be the correct dynamics of the system because it's just some kind of an estimate. Right? And then we use the resulting pi star to go back and get some more experience, right? Run some more trials, improve our p hat SA. and then re-estimate the value iteration. Now, one obvious optimization or a computational optimization is that when we start the value iteration in some loop, when we describe value iteration, we would always start the value function at 0. So instead, what we can do is in the next iteration, when we start value iteration, we can initialize the value function at the same point where we had converged in the previous function instead of starting it at 0 all the time, right? And that will allow us to have a much more faster convergence in step C. Any questions on this? Cool. Yes, question? Step D. So step D, you're saying update pi to be greedy with respect to VT, and that is this step 2. You get some V and you get the pi corresponding to that V. So value iteration and policy iteration, they assume that we know the dynamics, right? And when we don't know the dynamics, what the exaction transition probabilities are, you can think of that as one relaxation of the MDP where we don't know what the exact transition probabilities is, and that gives us this algorithm. This algorithm where we are simultaneously learning the dynamics, learning the model, and also performing value iteration according to the learned dynamics. Next, we will see another relaxation, which is, thus far we have limited our study to cases of or the types of MDP where the states and the actions were discrete and finite, right? We were limited to finite state and finite actions. Now, what happens when the states is continuous, right? What happens if the set of all possible states is continuous? For example, in the inverted pendulum problem that you'll be seeing in your next P set, the position of the pendulum, which you're trying to maintain it upright, the state of the pendulum can be represented by the angle it makes from the horizontal floor or the horizontal table, wherever it's placed, right? And that angle is continuous, right? So in kind of reality, the state of the pendulum or the state of your system or your agent is continuous. And what do we do in that in such situations? One obvious answer, or one simplistic approach, is what is called as discretization. In discretization, the idea is pretty simple. Supposing our state, so assume that this is the S space of, say, the inverted pendulum problem. So as a reminder, in the inverted pendulum problem, we have a cart, right, that can move along one direction, and on top of that we have a stick that we're trying to balance, and the stick could tilt this way or it could tilt this way according to the dynamics of the system, right? And if it is tilting this way, then we want to have a policy where we recognize that when the angle is tilted to the left, then we want to move the cart to the left. So the cart has actions move left or move right, like two actions, and the state can be any possible angle and any possible velocity, any possible position of this cart, right? So assume we have angle and velocity, right? So this space represents the set of all states that the system can be. However, the algorithms that we've studied so far are all designed for finite state and finite actions, right? So a common technique in such cases is to discretize your state space into discrete parts. Right? So what used to be a continuous problem, by discretization we can turn it into a discrete problem or a discrete setting, and we generally have some kind of a bound on the state space. For example, angles are kind of limited between 0 and 180 degrees. So there is a natural boundary for, even though it is continuous, there's a natural boundary on both sides. And similarly, the velocity can be bounded between 0 and the maximum velocity the cart can go, whatever, 10 miles per hour, so some such thing, right? And then we can discretize this state space into a discrete number of actual states, or the discrete number of virtual states that we'll be working with. This question?
So you in the, let's say in the preset you will have programmed it with, like, let's say some laws of physics, right? Like there might be like some differential equations which will have to, and for the state space we can also exploit some kind of symmetry, right? Like, so we don't have to.
Yeah, we could. So the question is, we can limit this more using domain knowledge like symmetry and whatnot. But that's not the point here. So the main concern with such approaches, which we're coming to next, is once we come up with a discretized state S prime or S hat, which where S was continuous, and this is discrete. So this is the discretized version of S. A common problem that we will see is, there are basically two problems. So the first problem is, so the first problem is, now what happens? So let's kind of switch back to supervised learning and linear regression, right? Let's step away from reinforcement learning for a brief moment. So if we had a data set like this, right, what kind of a model would you try to fit? Supposing this X and this is Y, what kind of a model would we try to fit? Linear, right? So this looks like a perfect perfect textbook case of a data set where linear regression would work very well, right? Now, in linear regression, we would just fit a straight line through this. However, if we were to perform discretization and learn the appropriate Y value within each discrete unit, we would get something like this, right? Right? Which means now we are, if we discretize it into bins and take the average in each bin to be the estimator for that bin, right? That's essentially what we are doing from moving from a continuous state to a discrete state by discretizing. We would get a hypothesis like this. However, this is pretty bad because first, it is much more complex, right? The number of parameters we need is the number of bins that we are breaking this down into. And further, we are not getting any kind of generalization. Now, what happens if our data set had some examples here and some examples here, and we did not have any examples here? Right? Discretization would just not work because we have never seen what happens in this bin. So in these regions, we would have 0 examples, and discretization is a pretty bad thing to do in such cases, right? Instead, we would rather have a simple straight line, right, which uses a much smaller number of parameters, and also it can interpolate well in regions where we don't have a lot of examples, right? So this idea of having some kind of a fitted function not only reduces the number of parameters that we need, but we also get some amount of generalization into regions where we don't have a lot of examples, right? And that's the idea that we're going to look into next. So as far as your homework problem is concerned, we will actually be solving it with discretization, and that's because it's a simple problem, and that's it's the purpose of the homework is to give you a framework to understand value iteration and estimating the transition probabilities, etc. However, in larger problems, in more complex problems, discretization usually is not the first step that you can that you use. In some cases, you do use discretization, but there you would need to kind of use some. You need to heavily use the domain knowledge of the problem space to reduce the dimensionality. Right? So, with discretization, one problem is this. We need to break it into multiple bins, and it does not generalize well. The other problem with discretization is what's called as the curse of dimensionality. Which means, suppose we have a state space of, let's call it 6 states. So let's say we have things like the supposing it's you're trying to learn a helicopter, then the number of states that you have are like the x position, y position, z position, and the angle at which the helicopter is pointing to. So it's like how upward or downward the helicopter is pointing to, or so you have 3 different angles: the angle at which the nose of the helicopter is pointing, the angle at which it is turned left or right, and there's one more angle which I'm not familiar with flying helicopters, but anyway, so you have different kinds of angles and different velocities, x, y dot, and z dot. So what's the velocity along the x-axis? What's the velocity on the y-axis? What's the velocity on the z-axis? And all the angular velocity. So theta dot, phi dot, psi dot, and I think I'm stop psi here. Right? So 1, 2, 3, 4, 5, 6 plus 6. So you have 12 different coordinates in your state space, and they're all continuous, right? And if you were to discretize them, right? Let's say you were to discretize them into each thing into say 10 units, right? You would essentially get 10 to the 12 number of discretized states, right? So each coordinate of your state space is continuous, and let's say you discretize them into 10 units or 10 bins, then the total size of your state space is essentially 10 to the 12, right? And that's pretty massive, and it is exactly this kind of an explosion in states that is that you get due to discretization that is called the curse of dimensionality, right? And it is. And that's probably one of the biggest limitations of discretization, because the number of states, as you add the number of components in your state space, it just explodes, right? And that brings us to what is called as the value function approximation. So in value function approximation, we now want to work in a setting where S is continuous. S is continuous, and we don't discretize. Right? And in this case, the most common setting is to have some kind of a simulator, right? So you have a simulator and in this simulator accepts some state S t, some state A t, and you get S t plus 1. Right? So assume you have some kind of a simulator where it takes as input the current state and the action and outputs the next state. Right? And the biggest difference between this and the previous model that we were working with was that in the previous model we had a finite number of states, right? And we had a multinomial kind of a distribution over the next state for every state and action pair. But over here the number of states is continuous, and we have in place of a multinomial kind of a model. Now I'm referring to the collection PSA as a collection of multinomials. In place of a multinomial which worked well in the discrete setting, we instead have, assume we have some kind of a simulator where we feed a real valued input and some action, and you get output as some other real valued state. All right, and these simulators can be, are generally, things like, physics simulators are commonly used. If you're working in some kind of a game playing scenario, then the game engine itself is the simulator and so on. Right, and now what we want to do is basically try to do the equivalent of this in a continuous space, right? So you want to kind of transform this into a continuous setting. This worked well because we were just counting, and it worked well because we could count discrete things. However, now we are in a continuous state and counting doesn't work anymore, right? And here we're going to use learn this simulator to the extent possible. And what do I mean by that? What I mean by that is we are going to make an assumption that st plus 1 is equal to some function of st at, right? And this relation, a common thing, for example, what we could do is assume f of assume a linear form for this relation, which means f is linear. So a is t plus b at, where a is a matrix and b is another matrix. And you can think of supposing S is in, let's say, Rd. Now A is therefore in R d by d, and similarly if A is in R, let's call it R P, then B is in R d by P. Right? And for those of you who have some background in electrical engineering, you might recognize this as a linear dynamic system, right? You have some particular state and you're taking some action, and the action and the state have this linear relationship to decide the next state, right? And assuming that your environment has this kind of a linear dynamical relation, we can then do the equivalent thing of this, which is, what shall I erase? Probably erase this. Which is follow some policy and run against, basically get some experience against this simulator. 1 E0 1 S1 1 E1 1 S2 1 1 S1 and another trial S0 to A02 and so on. So what's happening here is these are trials that we are running according to some policy against the simulator, right? And from this we collect S's and these S, A, S prime triples. So SA got us to S prime. This is one example. And SA got us to the next X prime. This is another example, and so on. And we can collect this data set of SAS prime triples, and then define a loss function J of A comma B is equal to sum over I equals 1 to n, assuming we do n trials, and just to make the math simple, assuming we are terminating all of them at ST, right? After you take t time steps, let's assume we just terminate it, right? And t equals 0 to t minus 1. What we want to do is minimize the square error between st plus 1 of I minus a st of I plus b a t of I. Right? So define a cost function where the st plus 1 or the S prime is considered the true or the Y label, and this is your hypothesis, right? So this st plus 1, you think of this as Y, and this you think of it as theta and x, where theta is A comma B and x is S comma A. All right? And now once you have a loss function like this, you can solve it using gradient descent and recover A and B, where A and B are the parameters of this cost function. This question?
Can we think the function as policy? The function of st plus 1. I mean, let's say this function is the policy, right? Because it's taking S and A and giving us the next state.
So the question is this, can we think of this as a policy because it takes S and A and gives us the next state? So a policy takes as input the current state and returns as output the action that we need to take while we are in this current state. Right? So this, think of this as the dynamics of the system. Right? If you are in a current state and you take an action according to some policy, what is the new state that we are going to end up with? Right? Whereas a policy will tell us, if we are given the current state S, what should A be? That's the policy.
So in this set of the continuous state system, we are not considering policy as anything, as any parameter.
So the question is, are we not concerned about policy in a continuous state? The answer is yes. Right now we are still in the state where we are doing something that is equivalent to learning the model, and once we learn the model, we will plug it into some algorithm like this, where we learn the model and estimate value and policy. We are yet to construct the full algorithm. We are only addressing this part of the corresponding algorithm of the continuous setting. Yes, question?
So those two sums out there, so the first one is across trial and the second is within a trial, right?
That's correct. So first sum is across trials. The second sum is within a trial. That's correct.
And can you explain intuitively why that form, you called it a linear dynamical system, why that is a reasonable assumption, ST plus 1?
So the question is, why is this a linear, a reasonable assumption? It may or may not be a reasonable assumption. This is just an example of how, if you model it as A and B as a linear dynamical system, then you can have a cost function like this and learn a suitable, a suitable model. You can absolutely use a more complex model over here and minimize instead of AST plus BAT, you would have a more complex form here, and you can minimize it. That's totally reasonable to do.
Does any example come to mind where that makes sense?
We'll at this point, let's just assume that our model can be represented as a linear system. A lot of examples can actually do pretty well in this, and we'll see what some changes can be done to this to actually work in a lot more cases shortly. Right? Yes, question?
So in this case, like in the next step when we consider policy, it will be a function because we are giving a continuous value of S, which is the current state, and it will be telling us an action which will also be a real value.
So the question is, in a continuous setting, should the action also be real valued for the policy? It need not be. So you can have continuous states but still discrete actions. For example, if you're trying to balance a cart pole, your state can be continuous, where the states are angles and velocities, but your action can still be discrete. It can be move left or move right. So you can having continuous state does not mean your action also have to be continuous. In cases when the action is discrete and state is continuous, your policy will take continuous input and output discrete.
But it will be a function of some kind, right? The policy, because it's taking input of real value.
Yes.
Parameter. When we compare it to the previous examples, policy was just a matrix of S and A's.
Mm-hmm.
Now it will be a function.
Yes. Now policy will be some kind of a function. Yes. So policy, so one thing to notice, should a policy always be a function? So if you see this relation over here, so what you do in, so the policy, if you think of it as something in this form, right, the induced policy according to some V, then it need not actually have any particular functional form, right? It can just evaluate the V function, which takes a continuous input at different possible according to different possible actions, right? And you can get the next state according to the dynamical system that we constructed, right? And evaluate the value function at the new states, and you can just take the argmax, right? So the policy can be kind of implicit or induced according to some value function and some model. It need not always be an explicit functional form. All right. So then if we minimize this cost, so A hat comma B hat equals argmin of A comma B, then A hat and B hat will be our learned model. By model I mean what we have learned about the way the world works. This A hat and B hat is, you can think of it as the equivalent of P hat SA. Right? So P hat SA gave us a way to relate state and action to the next state, and here A hat B hat gives us a way to relate state and action to the next state. Right? This question?
Previously with P hat SA, you gave the example that there is certain element of stochasticity, right? After you learn A hat and B hat,
we'll come to stochasticity next. Yeah. So the model that we learned with the linear model that we learned was deterministic in some sense, that S t plus 1 is equal to A hat S t plus B hat A t, right? So once we minimize A hat and B hat according to this cost function, we will recover some A hat and B hat, and the prediction that we are going to make for the next state is according to this, right? But in general, so if we just limit ourselves to this, we would call this a deterministic model. But in reality, it's always a good idea to have some kind of stochasticity in your model, which means we want to predict S t plus 1 be equal to A hat S t plus B hat A t plus some epsilon, right, where epsilon comes from, a common choice is a normal distribution that has mean 0 and some covariance sigma. And it's also possible to learn this sigma from data. Basically, the way to think of this covariance is to you can estimate this covariance as 1 over n times 1 over t minus 1 s t s I t plus 1 minus A S T I plus B A T I B A I T transpose, right? So this is just the, if you've done this with GDA, this is something you should be familiar with, which is the maximum likelihood estimate of a covariance will be just the residual transpose across all the examples. Yes, question?
Why the t minus 1?
Because this is we're summing across all n and t, right? Right. So it is. In general, it is considered a good practice to build stochastic models where the prediction that we make about the next state follows this format, where for each prediction we sample an epsilon according to this distribution, and this distribution is learned where the covariance is estimated this way. So you can think of sigma hat as this. This question?
Yeah. So let's say on like the p-set or like in real life, how do you know when to stop that step? Like how much, like when do you know your estimates of A, B, and sigma are okay? Like is there any, let's say like you said that in the pendulum example, will you give us a limitation of like how many times we can query that?
So the question is for the p-set, you will not be doing any of this for the p-set, right? In general, the question is, when do we know we have collected enough evidence or experience? When this, in case of the discrete setting, you can stop when the v stars that you get at the end of each iteration starts converging. So the question is, you can phrase the same question as when do you know you have your estimate of p hat SA is sufficient, which is the same as when is the estimate of A and B sufficiently correct. And in this case, you can consider it as sufficient when this overall, this outer loop converges.
For that part only, like let's say on the p-set, how will we know like how many trials, how many episodes to query?
Yeah, so again, so for the p-set we have instructions given in the p-set itself. You can follow those instructions, and the idea in general is that your value function stops changing over time, right? That's a good sign. Right? So instead of constructing a deterministic model, it is always better to construct a stochastic model where the noise that you want to induce into the stochastic system can also be estimated using MLE. Right? A and B were estimated using MLE, and then we can also estimate the noise that we want to induce, which is kind of consistent with the errors that we are making, can also be learned this way. And when you're making the next prediction, just sample some noise according to that covariance and make your a noisy prediction every time. Okay? So this is how we would learn a model. So learn a model in continuous setting, right? Now let's see, after having addressed modeling modeling the environment itself as continuous, now what do we do about the value function itself? Because if you remember, for example, in this example, S comes up in the model, in the transition, and S comes as an input to V, right? In the discrete setting, V was just an array where we had where the length of the array equal to the number of states that we had, and the transition function or the environment was also a matrix where the number of states was continuous, so it was just a matrix. But now when we move to continuous states, the transitions or the environment or the model can be made continuous. Next we need to make the value function also continuous, right? And a common approach for doing that is to first think of our value function as V of S is equal to R of S plus gamma times max A expectation of S prime from PSA V S prime. Now PSA, you can think of PSA from this model as PSA is equal to some normal distribution where the mean is AS plus BA and covariance is the covariance that we estimated here. Right? So you can think of this as PSA where you sample the next state according to this, and so this can now, you can think of it as R of S plus gamma times max A integral P of PSA of S prime times V of S prime ds prime, where this is the Gaussian PDF. Right? So you can think of the value function as this analog of the discrete version, where the expectation is now over a continuous random variable instead of a discrete random variable, right? And the input to the value function is also a continuous value, right? And this identity is again is also called the Bellman equation, because it's Bellman equation. It's just the continuous version of the discrete setting. However, what we end up doing in practice is to use what is called as a fitted value function, or the value function approximation. Value function approximation, where we say V of S is equal to, for example, in this case, let's assume a simple theta transpose phi of S. Right? Just like linear regression with some kind of a feature map, you construct a feature map of your state space using whatever domain knowledge you have, and assume you have some kind of a a linear relationship for the value of a function based on the state that it's in. Right? And with this assumption, what we want to do is try to come up with a value function, a v function that has this form, but satisfies the Millman equation, right? Which was basically what we did with the value iteration in the discrete case, and we're going to now do the same thing with the continuous in the continuous case, right? So this gives us an algorithm with these two assumptions that looks like this. So now this is an algorithm where we are using continuous state with some model, where the model in this you can assume it to be a linear dynamical system with where you have the A and B matrices, and we are doing value function approximation, right? So here this was S t plus 1 equals A S t plus B A t. And the value function approximation, where we have V of S is equal to theta transpose phi of S. So this algorithm is basically an adaptation of this algorithm, but to the setting of continuous states and value function approximation, right? Over here, both the states and the value functions, you can think of them as non-parametric, which means we did not have a family of some kind of a family of functions for V or PSA. However, these are parametric in the sense that the transition or the model has A and B as the parameters, or if you're having epsilon, it has sigma as also a parameter, and the value function has theta as the parameter, right? So it's basically an adaptation of that algorithm into this setting. So step 1, randomly sample n states, call them S1, S2, Sn in S, to initialize theta to be 0, and step 3, repeat until convergence. Now there is an inner loop here for I equals 1 till n, the inner loop. Is there a question? So for I equals 1 through n, oh sorry, there's an inner loop within this as well. For each A in the action space, sample S1 prime till Sk prime from P Si A, right? So in this case, it could be, for example, the normal distribution with A S I plus B A and covariance sigma hat, for example. and then set QA is equal to the average 1 over k, right? J equals 1 through k R of S I plus gamma of V of S J prime, again where here V of S is equal to theta transpose phi of S, right. So we do this for each action and then continue it over here. Set yi equals max A Q of A, and that ends this. So let's call this as a start A, start B, and start C. So this is finish C, this is finish B. And then set theta hat equals arc min theta I equals 1 to n theta transpose phi of Si minus yi square. This is finish A, right? So start A ends with finish A, and start B ends with finish B, and start C ends with finish C, right? So what's happening here? First we start by initializing the theta of our value function class to be some to some value, theta equals 0, and then we repeat this iteration over and over, where first for each example our goal is for each I in so for each of the states that we have sampled randomly, we want to come up with an estimate yi for each Si, right? That's the goal here of the outer loop. So for each of the states that we have sampled, we want to come up with yi, which is our, think of yi as the label for V of Si, right? So we want to construct an estimate of V of Si for each I, and that's what the start B to end B achieves. And the way we go about doing that is for each Si, take all the possible actions starting from Si, and for each action we sample k next states. So for each Si and action we get k number of next states sampled according to the transition, right? And this transition we are going to use the learnt model. It could be a linear dynamical system, it could be anything more complex. And then we're going to define this quantity Q of A as the expected value of taking that action from that state, right? So Q of A is the average of R of Si plus gamma of V of the next state, and averaged across all the J's, right? Does this make sense? So we're going to start with some random state S, and from this S we're going to take all the possible actions A, A1, A2, A, in this case, capital A. We're going to take all the possible actions from each state, and for each action that we take, we're going to get k number of S prime, so S prime 1 until S prime k for each action, right? And similarly, we're going to get S prime 1 until S prime k for each action, for each state, right? And then from each of those final states, we're going to evaluate the value according to the current estimate of the V function, right? So the current estimate of the V function uses the theta value we have so far, right? In the first iteration, it's going to be 0. After that, it's going to be something else, right? According to the current estimate of the V function, we're going to estimate we're going to use the evaluation of these states using the current estimate of the value function, and we're going to construct this Q value as the expected value of taking this action. This function? Yes, question?
Phi of S is feature map for states, right?
Yes, phi of. So phi of S is just a feature map, and you define phi of S according to your problem setting, right? So in homework 1, we define feature maps with sinusoidal, squared, polynomials, etc. You define some such feature map for your state space. Yes, question?
I didn't quite understand. Can you explain that design choice for V? Like, why did we say V of S was theta transpose V?
I'll come to that. For now, assume V has this linear relationship, right? So what we do is, for each S, we take all the possible actions, and from each possible action, sample new states, and for each of those new states, calculate the value of each new state according to the value function approximation that we have, right? And then take the average, and this Q is now an approximation for, right? So Q is therefore an approximation. Q of A is therefore approximately R of Si plus gamma times expectation of S prime in Q, S prime of P S A of V of S prime, right? So the Q value that we constructed is approximately this, and the reason is because, so R is just a constant, so you can actually take out R from this averaging, right? And what remains here, what we are seeing here is therefore a Monte Carlo estimate of this expectation, right? It's a Monte Carlo expectation because we are approximating the transition with k items, and it is also an approximation of V because we are only using the current estimate of the value function with this functional form. Yes?
So Q of A is the estimated, is the expected reward we'll get, like, until the
Expected long-term value for taking from this state for taking action A.
So shouldn't Q be S comma A?
Yeah, so you can think of it as Q of S comma A. That's fine too. So yeah, Q of S prime, right? That's fine. So right, so this Q is an approximation of the right-hand side of the right-hand side of the Bellman equation, right? So now we define Yi as the max over Qi. So Yi is now max A of Qi of Qa, and Qa is basically R of Si plus max A of gamma times the expectation of S prime from PSA of Vs prime. Right? So yi, which was max over qa, is max over, max with respect to a of this thing, and therefore it is, when we apply the max, r comes out of the max because there's no a term in it, and it's max over a of this term, right? And this now looks like the Bellman update operator, right? Or the Bellman backup operator. So according to the Bellman backup operator, we should have set V of S to be equal to this, right? But our V takes this parametric form. So we just cannot set V of S to be some value, right? Because V is not an array and we are not setting the Sth element to be some value. What we instead want to do, because we are in this value function setting, is to minimize the distance between yi and V of Si. And that's exactly what we're going to do. We're going to minimize the distance between yi and V of Si. This question?
Why is it that V is not a vector of size S?
V is not a vector because S is continuous. We are in the continuous setting, and we are approximating this continuous function with this linear form.
So if S is continuous, then what meaning does Phi of S have?
Phi of S is just a feature map for some S.
But S, okay.
So the way to think about this is to see the similarity with the Bellman backup operator. Right? In case of the Bellman backup operator, we would have V of Si to be equal to R of Si plus max of A over this expectation of V of S prime. Instead, because we are in this fitted function setting, we are going to approximate this expectation with the Monte Carlo expectation. That is, this is the Monte Carlo expectation. So this expectation is going to come in here. R of Si is just R of Si, and this will evaluate to some Y of Si, which in the discrete setting we would have just set it as the vth element or the sth element of the V array. But instead we are in a fitted function setting, which means we want V of S to evaluate to Y or as close to Y as possible, right? Which is why we minimize the squared error between phi of phi. So think of this as V of Si, right? And this is the RHS of the Bellman backup operator. Right? So what's happening here is that, first of all, let's see a few things, the way it is similar to this. So first of all, here we are in the discrete setting, we were learning both the model and performing value iteration kind of intertwined. And we are trying to do something similar here, in the sense we are first, in this setting we are learning the A's and B's, the dynamics, which is equivalent to this first. We are not doing it intertwined, but we are first learning the dynamics, and using those dynamics we are now performing value iteration using the Bellman backup operator, but we are performing it in such a way that the Bellman backup operator is working with these fitted value functions, right, instead of the true value functions. And another way to kind of understand this better is if you remember value iteration, so S1 through SD, right? In the fitted in the discrete setting, we had, supposing this was V star, right? We start with some random initialization V naught, and apply the Bellman backup operator to get V1, and we would keep getting closer and closer where each hop was one application of the Bellman backup operator, and the Bellman backup operator was a contraction mapping, so no matter where you started, you would converge at V star. But now in this setting, the space of value functions is somewhat limited. We are limiting ourselves to only those that can be expressed as a linear combination of the feature maps of S, which means this whole algorithm is kind of limited to some set of, think of this as set of all V, which can be such that V of S equals theta transpose phi of S. Right? This family of functions cannot represent all the possible functions in this functional space. Right? So we're kind of limited in that sense. And if we start with some value function over here, and we apply one iteration of this fitted value algorithm, fitted value iteration, it will give us, so if we are over here, let's call this V of t, the fitted value iteration might give us yi such that yi is over here, that it might be outside our functional space, the set of yi's, right? So we ideally want V of Si to be equal to yi, right? We want V of Si to be equal to I. We want this to be 0, right? But this y may be outside our functional space, and therefore when we perform this minimization, we are going to get the projection of yi onto this subspace, right? That's exactly what happened in linear regression. We're going to get this function over here, which is the projection of y onto this space, the nearest point in our family of functions that is nearest to y, right? And then we're probably going to keep hopping, by keeping ourselves within the family of the v functions of this parametric space that we have defined, and get as close as possible to V star. Right? That's what this algorithm will do us. This algorithm does not have the convergence guarantees of the discrete space setting. In the discrete space setting, the Bellman backup operator would take us to the true V star after a certain number of trials, whereas in the fitted value functions, we have limited ourselves to some space, and V star might be out of the space. There's no guarantee, and there is no guarantee that this algorithm will converge. But in practice, it generally tends to work well. This question?
Is it saying like RB resides in some lower dimensional subspace in the bigger state space?
So think of this as some kind of a functional space. Don't think of this as just think of it as some functional space where the set of all functions that can be defined in this form is limited to some kind of a set.
Can't that problem be solved by coming up with better features?
Yeah, I'm coming to that next. Yeah, so your V star can be outside the set of all functions. Yes, question?
Is this assuming the actions are still discrete?
Yes, here we are still assuming actions are discrete because we are performing a max over the different QAs. We are still assuming actions are discrete. Good question.
This algorithm will evaluate the projection of V star on this functional space.
Yeah. Right. The fact that we are minimizing this, think of this as the resulting theta transpose Si after minimizing this squared error. The result, once you do this, so V hat of S is equal to theta hat of phi of S. So this is essentially the projection of y onto the nearest point in the function space. Yeah.
Also, why are we not using phi s such that it belongs to that space? Because V star is surely.
Yeah. So the question is, that's something I'm going to address next. Right. So there are we've seen two kind of extensions to the standard policy iteration and value iteration so far. One extension was when we don't know the model, when we don't know the transition probabilities, we estimate it from data, right, PSA. And the other extension that we saw was to move on to this continuous setting from discrete setting. And once we move into continuous setting, the number of parameters we have can potentially be infinite, and therefore we limit our expressivity to some kind of parametric family model, right? And once we are limited to this parametric family of value functions, which we call as value function approximation, we then define an algorithm which is, kind of similar in spirit to the value iteration, right? It is similar in spirit because we are performing the same kind of updates, except when we are in the value iteration, we could just set the value that V of S needed to evaluate to. However, because we are now limited to a parametric family, what we do is minimize the loss between what our hypothesis can predict and what the right answer should be, right? Now there are, based on these two extensions, we can, so this basically kind of marks the end of what's kind of in syllabus. Let's see how we can, some of the other concepts in reinforcement learning and how you can think of the other concepts that you may come across as extensions to what we've seen so far, right? So in reinforcement learning, in the broader space, right, we can think of two approaches in general. The two approaches are approaches based on value functions and approaches based on policies. So value function based approaches versus policy based, right? So in the simplest setting, right, when everything is discrete and finite, it's basically the value iteration, and the policy based approach is basically the policy iteration, right? And as we move on to more, in terms of the complexity hierarchy, when we move on to infinite state space, right, we get the fitted value iteration. So fitted value iteration is basically this algorithm that we saw, right? And in both these algorithms, we call both these algorithms as model-based algorithms. We call them model-based algorithms because we constructed explicit versions of the way we believe that the model works, right? It was either in the form of the PSA transition matrix, or it was in the form of this linear dynamical system where ST plus 1 was distributed according to a normal equation, right? Either we constructed a dynamical system approximation of the model, or we used directly the PSA transition matrix for the finite state case, right? However, we can move on to model free methods. In the model free methods, right, we acknowledge that we don't know how the model, how the real world works, or how the dynamics of the system works. But we also say we don't care how it works. Whereas in model-based approaches, we acknowledge that we didn't know and we try to learn it. Right? In model-free approaches, we say we don't know how the world works, we don't know how the transitions happen, and we don't care. And the way we say we don't care is by coming up with what is called as a Q function. Right? And the Q function is basically, think of it as Q of SA to be the value, the expected value of being in state S and taking an action A. Right? And the reason why, even though it seems like a simple addition of an action, it is fundamentally very different. The reason why it's very different is because supposing we learned V star of S, and we don't know how the dynamics of the system works, but we still somehow figured out the optimal value of being in each for some state. Now, how do we decide what the action is? There's no way, because we don't know which state we will end up in by taking some action, because we don't know how the dynamics of the system works. Right? So knowing V star is insufficient if you don't know the dynamics of the system. And the way we go about that limitation is to instead learn these Q functions, which is basically the Q function is basically telling us what is the expected sum of all future rewards, discounted sum of future rewards, if we are at state S and take an action A. We don't know what state we are going to end up in, but if we take this action from the state, the Q of SA tells us what's the expected sum of future rewards. Right? We just stay agnostic to which state we are going to end up in, and directly assign a value to taking an action at a given state. Right? And these techniques are called Q learning. And we can apply Q learning, function approximation, to Q learning as well. We saw function approximation applied to value functions, and just in a very similar way, we can perform function approximation for Q values or for the Q function. Right? And we saw an example where the family of the function space with which we performed approximation was linear, but there's nothing stopping us from using more complex functions. Right? So this this approximation of the value function using a linear function, this could have been something much more complex. We could have used a neural network here, where the input was S and the output was the value at the last layer. And when we are minimizing this, use backpropagation and minimize the loss with respect to the parameters of a neural network. Right? There was nothing that stopped us from doing it. And when we use neural networks as the function approximators for either the value function or the Q function, that basically gives us the field of deep RL, or deep reinforcement learning. So you can use deep reinforcement learning by using neural networks as approximators for your value function or the Q function. There is another. There are other approaches or other kinds of classifications you can think of. In the finite case, the way we evaluated the value function was using something called as exact method. So the Bellman backup operator, when you apply it over and over again, you get the exact V star. And there are other approaches where you can use Markov chains or Monte Carlo approaches, not Markov chains, Monte Carlo approaches, or you can use something called as TD learning or temporal difference learning. TD learning, so in Monte Carlo approaches, what we do is we take some value, we take some policy, and just follow that policy until the end, until we reach a terminating state, and then calculate the discounted sum of rewards and use that as the estimate of the value function. That is, actually try it out and measure how much total value you got and average it across multiple runs. That's Monte Carlo based. However, the limitation with that is that you got to follow the policy until things terminate. Right? Whereas there's something called TD learning or temporal difference learning that is something in between exact and Monte Carlo. And in fact, in practice, TD learning is what's used most commonly. Right? If you're using so TD learning is in fact something very similar to this. Right? What we did over here is something very similar to TD learning. That's TD learning means temporal difference learning. That's probably all that I wanted to. So there's probably one more thing I want to say. So there is another kind of line of classification you can use for a reinforcement learning algorithm. There's something called on policy versus off policy methods. So in on policy methods, you're trying to learn the value function by staying on the given policy, whereas with off policy, you're looking at data that was where the trajectories were obtained from some other policy, and you try to learn the value function of a new policy that you're trying to come up with. And this off-policy method has, for those of you who have a more statistical background, off-policy methods in reinforcement learning has a strong connection to causal inference. Right? Because in causal inference, you're seeing some observational data, and you're trying to work your way backwards to decide, what would have happened if we had taken some other action instead, right? And that has kind of pretty strong ties to causal inference, where here we are, observing a sequence of actions that were taken according to some policy, and we are trying to answer what would have happened if we had tried some other policy instead, right? So reinforcement learning is a vast area of machine learning, and in fact, probably reinforcement learning has its roots mostly in the field of electrical engineering called optimal control, and I think its history is probably older than machine learning in general, and so it's a pretty vast field, and there are lots of ways in which you can use machine learning. And the most common way, or the most popular way, where machine learning and reinforcement learning are kind of coming together is using more expressive function approximation methods to approximate either the value function or the Q function using neural networks or deep learning techniques. And also there is you can also use neural networks for policy-based methods for something called policy iteration, though we didn't cover any of that in this course. All right, so that brings us to an end to reinforcement learning, and starting Monday we will start the next chapter, which is unsupervised learning. Right, have a good weekend.